incredibly timely right now. AI is everywhere, isn't it?
Oh, absolutely. Generating text, images, drafting emails.
Trying to plan our lives even.
Yeah, it feels like it's just exploded.
But here's the thing. Taking these really powerful models, these foundation models, as we call them now, and actually making them into reliable, useful apps, things people really use.
That's a whole different challenge. It's not just about the cool demo.
Exactly. It's a new kind of engineering, really.
It truly is. Making that jump from a neat proof of concept to something production ready, something that actually works consistently and you can maintain, that takes a specific skill set.
Right. And that's what this deep dive is all about, AI engineering. How do you actually build applications with these foundation models?
It's the million-dollar question, isn't it?
It is. And to help us unpack it, we're digging into Chip Huyen's book, AI Engineering, Building Applications with Foundation Models. It's a really comprehensive guide.
Yeah, it's a great resource. It cuts through a lot of the hype and gets down to the practical stuff, the how-to, but also the watch out for this.
So think of our mission today as like a guided tour. We'll hit the key ideas, the techniques, the engineering hurdles you absolutely need to grasp if you want to build things with these models.
Consider it your shortcut to getting up to speed on this really critical, fast-moving field.
Ready to get into it?
Let's do it.
Okay, let's start big picture. What is AI engineering, fundamentally?
Well, the source makes a key point. A lot of the traditional ML engineering stuff, still totally relevant. It's the foundation.
But these new foundation models, because they're so massive and capable, they bring new opportunities, but also, importantly, new headaches.
Exactly. New challenges that need, new solutions. It's not just business as usual.
And often, a real-world system isn't just one big foundation model doing everything, right?
Not at all.
Yeah.
You might have a mix, maybe some classic ML models for certain tasks, working alongside a foundation model for, say, text generation. It's often a hybrid system.
An orchestra, as the source puts it.
That's a good way to think about it.
And crucially, before you even think about code, the book stresses these vital upfront questions. Like, first, do we actually need this application?
Seems obvious, but easily overlooked in the excitement.
And then, is AI really the right tool here?
Yeah.
Or is there a simpler way?
And the pragmatic one.
Nah.
Do I have to build this? Maybe something already exists that does the job.
Seriously, asking those questions first can save so much pain later.
Oh, absolutely. Avoids building things people don't need or that are just technically cool but not practical.
Okay, so assuming you've got good answers there and you are building, you need to understand the core concepts of these foundation models.
Right. What's actually going on under the hood, at least from an application builder's perspective?
First up, and this is huge, training data. The book is blunt.
Yeah.
Your model is only as good as its data, period.
And this has massive implications. For instance, most big language models, they work way better in English.
Why is that?
Well, think about where they get trained overwhelmingly. It's data scraped from the internet. And the internet is dominated by English content.
Ah, so the benchmarks, like MMLU, clearly show this language imbalance.
Exactly. It's a direct reflection of the training data distribution.
And what if your task is super specialized, like drug discovery or analyzing medical scams?
Then the general internet data probably won't cut it. That specific, crucial information needed for, say, understanding protein structures or spotting anomalies in an X-ray, it's just not likely to be in that massive web crawl.
So you need a dedicated data strategy for those domains. You can't just plug and play.
Absolutely not. Data is key.
Okay, next concept, scale and architecture. These models have gotten enormous.
Mind-bogglingly big. We went from millions of parameters to hundreds of billions, even trillions now. The book mentions 100 billion is considered large today, but who knows next year?
And the reason they need so much data is tied to this scale, right?
Yes, more parameters mean the model has more capacity to learn complex patterns, but it needs the data to actually learn them. More capacity requires more fuel, essentially.
And architecturally, it's been all about the transformer for a while.
Since about 2017, yeah. The transformer architecture, especially its attention mechanism, has been dominant.
But the book mentions things might be shifting slightly. Alternatives emerging.
It does. It mentions models like RWKV, which uses an RNN-based approach. People are exploring different ways to handle long sequences of information, maybe get around some transformer limitations. Still mostly transformers, but it's not the only game in town anymore.
And these models aren't just text anymore, right? Multimodality.
Huge trend. Models like GPT-4V, Claude 3, they understand images and text.
And it's moving beyond that. Video, 3D.
That's the frontier, making AI understand and interact with the world through multiple senses, just like we do. It's a really exciting area.
Okay, now this next one, sampling. The source calls it maybe one of the most underrated concepts.
I completely agree. It's fundamental to understanding why these models behave the way they do.
So sampling is how the model chooses its output, like word by word.
Exactly. At each step, the model calculates probabilities for all possible next words or pixels or whatever. Sampling is the process it uses to pick one based on those probabilities.
And it's probabilistic, not deterministic. That's the key.
That's the absolute key. Because it's probabilistic, you get weird behavior sometimes. Ask the same question twice, get two different answers. That's inconsistency, a direct result of sampling.
And hallucinations when it just makes stuff up.
That too. It might sample a plausible sounding but factually incorrect continuation because the probabilities led it down that path. Understanding sampling helps demystify these quirks.
So it's not always a bug in the traditional sense, but a feature of its probabilistic nature.
In many cases, yes.
Wow.
But the flip side, the positive side, is that this same probabilistic sampling is what allows for creativity.
How so?
It lets the model explore less common, more unexpected combinations. It can deviate from the most boring, predictable path found in the training data and generate something novel.
Okay, that makes sense. And as engineers, we can control this sampling process somewhat.
Yes, definitely. There are knobs you can turn. Temperature is a big one.
Higher temperature means.
More randomness, more creativity,
Hmm.
potentially more surprising or even nonsensical outputs. Lower temperature makes it more focused, more predictable, maybe more repetitive.
So it's a trade-off.
Always a trade-off. The book also mentions top K sampling, only considering the top K most likely options.
And top P, or nucleus sampling.
Right, that's a bit more dynamic. It picks from the smallest group of options whose probabilities add up to a certain threshold P. So if one word is highly probable, it might just pick that. If probabilities are flatter, it considers more options.
The takeaway is understand sampling, and you have more control over whether you want the model to be reliable or creative.
Precisely. It's your main lever for controlling the output's nature.
Okay, so a model gets pre-trained on tons of data. Then comes post-training. What's
Sure.
that for?
So post-training tackles two main problems with those raw pre-trained models. First, they're trained to predict the next word, which isn't the same as being helpful or following instructions in a chat.
Right, just completing text isn't the goal of an application.
Exactly.
Mm.
And second, if you train on, the whole messy internet, the model can learn biases, generate toxic stuff, or just give really unhelpful answers.
So post-training is about alignment, making the model behave in ways humans find useful and safe.
That's the core idea, alignment. It involves techniques like supervised fine-tuning or SFT.
That's training on good examples.
Yeah, showing it high-quality examples of conversations or tasks done well. And then there's reinforcement learning from human feedback, RLHF.
RLHF. That uses human preferences, right?
It does. You have humans compare different model outputs, which answer is better, and use that comparison data to train a separate reward model.
A model that learns what humans prefer.
Essentially, yes. It learns to predict which kinds of responses humans will rate highly. Then you use that reward model to further tune the main language model.
But the source mentions a challenge there. Capturing human preferences is tricky. People disagree, or preferences are subtle.
Absolutely. It's hard to distill complex human judgment into a single score. The example where the human preferred the losing response really highlights that nuance. It requires very careful data collection and ongoing refinement.
But these steps, SFT and RLHF,
Yeah.
they're essential to get from a raw, pre-trained model to something you'd actually want to interact with.
Indispensable for most real-world interactive applications.
Okay, so speaking of applications, what can these models actually do? The book gives a good overview across consumer and enterprise.
And the range is pretty staggering, which is why everyone's so interested in building with them.
Let's hit a few examples that stood out. Education is a fascinating one.
Yeah, initially schools were banning tools like ChatGPT, right?
Total panic mode.
But now the conversation is shifting. How can AI actually help learning?
The book makes this great point. Online ads are hyper-personalized, but education is often still one-size-fits-all. Strange, isn't it?
It is. AI could change that. Imagine summarizing dense textbooks, generating personalized study plans.
Or adapting materials, like if you're an auditory learner, ask the AI to read text aloud. Or explain a concept using analogies related to animals if you love animals.
Exactly. Or translating, say, a tricky math concept into Python code for a student who thinks that way. That kind of personalization is powerful.
Very powerful.
Yeah.
Okay, another big area, data organization.
This is huge for businesses, taking all that messy, unstructured data emails, PDFs, reports, images, even scanned receipts, and pulling out structured information.
Like names, dates, amounts from an invoice, or maybe key clauses from a legal contract.
Precisely. The source mentions the market for this intelligent data processing, or IDP, is projected to be enormous, over $12 billion by 2030.
Wow. And the Google Photos example is so relatable, having like 40,000 photos and needing AI just to find the picture of your dog.
It perfectly illustrates the problem of unstructured data at scale. And the Talk to Your Docs use case follows directly from that, asking questions about your own documents.
And finally, workflow automation.
This is about tackling those boring, repetitive tasks. For us as individuals, maybe booking appointments, planning a basic trip.
Things that just take up time.
Exactly. And for businesses, it's things like processing invoices automatically, managing sales leads, summarizing meeting notes, freeing up humans for more complex work.
These examples really drive home why this engineering matters. It's about turning that raw potential into actual tools.
Right, but building those tools, that's where the engineering challenges really kick in.
And the book dives deep into one of the toughest evaluation. How do you know if your AI application is actually any good?
It's notoriously difficult. The source points out many still rely on just, eyeballing it or a vibe check.
Which isn't very scientific.
Not at all. You need systematic evaluation, especially for production systems. The problem is, unlike traditional software with clear right-wrong answers, AI outputs are often fuzzy, creative, nuanced text or images. Defining good is hard.
So what criteria should we use for systematic evaluation?
The book highlights several. Factual consistency is a big one. Does the model make things up? Does it contradict itself or known facts?
How do you even check that automatically?
It's tough. Techniques involve checking against knowledge bases or even using other AI models as judges. The source mentions things like GP2 judge.
AI judging AI. Doesn't that feel a bit circular, tautological?
It definitely can feel that way, and the book acknowledges that limitation. It's an active research area. The thinking is that stronger models might be better judges, and maybe you can train smaller, specialized AIs to judge specific things like toxicity or factual accuracy.
But it raises that interesting question from the source. Can a weaker model reliably judge a stronger one?
Right, the analogy was great. Anyone can have an opinion on a song, but not everyone can write one. So using AI judges requires a lot of care and calibration.
Makes sense.
Yeah.
What other evaluation criteria are key?
Instruction following capability. This is critical. Did the model actually do what you asked it to do?
Like stick to a word count or output valid JSON.
Exactly. Benchmarks like IFEVL test this rigorously. And of course, safety criteria, checking for toxicity, bias, leaking private information, those are absolute musts.
Okay, so you have criteria. How do you use them to pick the best model for your application? The book warns against just trusting public leaderboards.
Yeah, those leaderboards often use really simple prompts, totally out of context. They don't reflect real-world usage.
So you need your own evaluation setup.
Absolutely. The key takeaway for engineers is design a custom evaluation pipeline. First, define what good means for your specific use case. Then connect those AI metrics like factual consistency percentage directly to business goals, like maybe the percentage of customer support tickets you can automate.
And don't just test on one data set.
No. Use multiple evaluation sets. Slice your data to check performance on different user groups or edge cases. The source mentions Simpson's paradox, how overall averages can hide really poor performance on specific subgroups.
And you need enough data for confidence.
Right. The book even gives guidance on estimating sample sizes for statistical significance. And you have to be vigilant about data contamination.
Making sure your test data wasn't accidentally part of the model's training data.
Exactly. That gives you falsely optimistic results. Leads to deploying something that fails in the real world. Evaluation is hard, but you have to invest in doing it properly.
Okay. Essential but hard. Got it. So you have a model, an evaluation plan now you build. Prompt engineering is usually the first stop.
Yep. Crafting the instructions for the model. The source says it's easy to start, but hard to do well.
It's like learning a new communication style, human-AI communication.
That's a good way to put it. Best practices include: be clear, be explicit, don't be ambiguous, give the model enough context.
Use examples. Few-shot learning.
Definitely. Show, don't just tell, sometimes. And a big one. Break down complex tasks, that whole think step-by-step prompt.
Yeah. Why does that work so well?
It seems to force the model to, well, slow down and work through the reasoning process internally, which often leads to better, more coherent outputs for complex problems.
And you have to iterate, right? You won't get the perfect prompt first time.
Almost never. It's a cycle of write, test, refine.
But prompting isn't just about getting good results. There's defensive prompting, too. Protecting your system.
Absolutely critical. You need to anticipate how users might try to misuse or attack the model. Things like jailbreaking or prompt injection.
Where users try to trick the model into ignoring its safety rules.
Exactly. They might embed hidden instructions, maybe frame a harmful request as a poem or a story, try to get it to reveal sensitive info, or execute unintended actions.
Like asking for a poem about how to hotwire a car.
That kind of thing. Or manipulating the output format to hide malicious code. The book also mentions risks like extracting training data.
Can attackers really pull private data out of a trained model?
Research suggests it's possible, though challenging. If the attacker knows specific details about data the model was trained on, they might be able to craft prompts to retrieve it. And there's the risk of the model just regurgitating copyrighted text it saw during training.
So defensive design is crucial. Okay, let's shift to a really important architectural pattern. RAG, Retrieval-Augmented Generation.
ARGI has become fundamental for so many applications. It directly addresses two big limitations of foundation models: their knowledge cutoff date,
Right, they don't know about current events.
and their limited context window. They can only pay attention to so much text at once. RA lets you feed them relevant, up-to-date information from external sources.
So you connect the model to, say, your company's knowledge base
Right.
or a database of recent news.
Exactly. At the time the user asks a question, you first retrieve relevant documents or text snippets from your external source. You can use classic keyword search like BM25 or newer semantic search based on embeddings. Then you take that retrieved context, bundle it up with the user's original prompt, and feed it all to the language model for the generation step. The model uses the provided context to answer the question accurately.
So the value is getting more accurate, timely, and domain-specific answers.
Yes, and often at a lower cost than constantly fine-tuning the model itself with new data. It makes the model's knowledge dynamic.
But our RAG itself needs engineering. Optimizing the retrieval?
Oh yeah. How do you chunk your documents? How do you rewrite user queries to be better for search? Do you need a re-ranking step to prioritize the best results? Optimizing RGA is a whole subfield of AI engineering now.
Makes sense. Okay, what about agents? Using models not just to talk, but to do things.
This is pushing the envelope. Giving the model access to tools, a search engine, a calculator, APIs to book flights or order groceries, and letting it figure out how to use them to accomplish a goal.
So the model becomes a planner.
Kind of. The basic idea is a loop. The model plans what to do, uses a tool act, sees the result, observe, and maybe reflects and adjusts the plan. Frameworks like React formalize this.
Sounds powerful, but also fragile.
It can be. The source is realistic about the challenges. Agents can make bad plans, fail to use tools correctly, get stuck in loops, or just be really inefficient.
And they probably need memory to keep track of things across steps.
Definitely. External memory systems are often required. It's a very active research area, but making agents truly robust for complex tasks still needs significant engineering work.
Okay, let's talk fine-tuning. This is actually changing the model itself, right?
Yes, updating the model's internal parameters, its weights, to adapt it to a specific task or domain. It's different from prompting or AGI, which work at inference time.
When should you consider fine-tuning? The book suggests it's not the first thing to try.
Generally, no. You'd usually explore prompting and RAG first, because fine-tuning is expensive. It needs a lot of high-quality, task-specific data, it needs significant computing power, and it needs ML expertise.
So you do it when prompting isn't enough, maybe for a very unique task, or to deeply embed specific domain knowledge.
That's typically the trigger. Or maybe to get the model to adopt a very specific style or tone consistently.
But there's a risk, the source mentions. Catastrophic forgetting. Sounds bad.
It can be. When you train the model intensely on your new task, it can sometimes forget how to do other things it used to be good at. Its general capabilities can degrade.
How do you avoid that?
Careful data mixing includes some general data along with your task data, or maybe train separate specialized models. The book mentions Bloomberg GPT as an example of a model heavily fine-tuned on financial data.
And interestingly, the source notes RG can sometimes beat fine-tuning, like for questions about very recent news.
Right. It highlights that fine-tuning isn't always the best solution. It depends on the problem.
Now, fine-tuning the whole model takes massive amounts of memory, but there are more efficient ways. PEFT.
Yes. Parameter-efficient fine-tuning techniques like LoRa are game changers here. Instead of updating all billion parameters, LoRa freezes the original model and trains only a very small number of additional parameters. It dramatically cuts down the memory and compute needed.
And QLoRa combines this with quantization.
Exactly. Using lower precision numbers during that efficient tuning process, reducing the footprint even further. PEFT makes fine-tuning much more accessible.
So it's practical for more teams now.
Much more so. The book also mentions model merging, combining fine-tuned models as another technique being explored.
Okay, whether it's for fine-tuning or even drag, data quality is paramount. This brings us to dataset engineering.
Back to data again. The source really hammers home the data-centric AI idea. Often, improving your data gives you bigger wins than just tweaking the model architecture.
And that quote is powerful. A small amount of high-quality data can outperform a large amount of noisy data. The Llama example.
Yeah, a relatively small model, Llama, fine-tuned on just about 1,000 really carefully curated examples, showed surprisingly strong performance, quality over quantity.
But getting high-quality data is hard. Annotation needs clear guidelines.
Very clear guidelines, and it's often iterative. You see how labelers interpret the task, refine the rules, relabel its process. The book also talks about data synthesis.
Generating new data. How?
Could be rule-based, could be using other AI models to paraphrase existing examples, translate them, generate variations, even create synthetic data like complex math problems for training.
Seems useful for augmenting data sets. But there's a big warning here. Model collapse.
This is a really serious concern raised in the source in recent research.
Who is it exactly?
It's what happens when models are trained primarily on data generated by other AI models, like an AI echo chamber. Over successive generations, the models start to lose diversity, forget outliers, and their performance degrades, potentially irreversibly.
Wow. So AI eating its own tail, essentially.
Kind of. It suggests that relying too heavily on synthetic data, especially recursively, could pose a long-term risk to improving AI capabilities. We need that grounding in real human data.
That's unsettling. Okay, moving towards deployment. Inference optimization. Making models run fast and cheap in production.
Crucial for any real application. The book explains the bottlenecks for language models. Processing the input prompt, the pre-fill stage, tends to be compute-bound.
Needs lots of parallel processing power.
Right. But generating the output, token by token, the decoding stage that's usually memory-bound, you're constantly accessing the model's weights and the KV cache.
KV cache?
The key value cache for the attention mechanism. It stores intermediate results to avoid recomputing them for each new token, but accessing it takes memory bandwidth.
And the key metrics engineers track here are latency.
Yep, time to first token, TTFT, how quickly the response starts, and time per output token, TPOT, how fast the rest comes out.
Throughput, how many requests or tokens per second.
Sure.
And utilization, how efficiently the hardware is being used.
MFU model FLOP's utilization is a common metric for that.
What are the main optimization techniques? Quantization.
Huge one. Reducing the numerical precision of the model weights using 8-bit integers, or 4-bit like QLoRa does, maybe even 1-bit models eventually, instead of 16-bit floats, saves a ton of memory and often speeds up computation.
Optimizing that attention mechanism, managing the KV cache better.
Absolutely critical for the decoding speed. Techniques like multi-query attention or group query attention help reduce the cache size and memory bandwidth needed.
What about speculative decoding? Sounds intriguing.
It is. You use a small, fast draft model to predict a chunk of tokens ahead. Then the big, powerful model just needs to verify that prediction, which is much faster than generating token by token if the draft was good.
Clever. And parallelism. Splitting the model.
Essential for large models. Tensor parallelism, pipeline parallelism, data parallelism, different ways to split the work across multiple chips or machines.
And prompt caching. Storing results.
Yeah, if you get the same prompt prefix, often in an ongoing chat conversation where the history is part of the prompt, you can cache the intermediate computations, those KV cache values, to avoid redoing them. Anthropic showed massive latency and cost savings with this.
So the whole toolkit of techniques to balance cost, speed, and throughput.
Exactly. It's a complex optimization problem specific to your application's needs.
Okay, pulling it all together, AI engineering architecture, the book shows how systems evolve.
Right. You rarely just deploy a model API call directly. You start simple, then add layers.
Like adding context augmentation to your RAG system.
Yep. Then maybe guardrails for safety checking inputs and outputs for harmful content or private data.
Adding caching for performance.
Exact match caching, maybe even semantic caching for similar prompts.
And as it gets more complex, monitoring and observability become vital.
Non-negotiable. You need to track metrics, logs, traces to understand what's happening. Detect drift. Are user inputs changing? Is the model's behavior shifting? You need eyes on the system.
Orchestration tools to manage all these moving parts.
Often necessary for complex pipelines. The key point is, building an AI app is building a distributed system with all the complexities that entails.
Right. And finally, even after launch, the job isn't done. Leveraging user feedback.
Especially for interactive AI, this is maybe the most important loop for improvement. The source stresses how vital it is.
What kinds of feedback are useful?
All sorts. Explicit feedback, thumbs up, down, ratings, corrections. Implicit feedback, analyzing how users interact with the responses. Do they copy the answer? Do they immediately try again?
And conversational feedback.
Right.
Just telling the bot it's wrong.
Yeah, users naturally providing feedback within the conversation itself, that wasn't right, or could you try explaining that differently? Gold dust, if you can capture and use it.
But collecting feedback has challenges too. Bias.
Big time. Users might prefer longer answers, even if they're less accurate. There's recency bias. Getting representative feedback is hard, and building the systems to collect, process, and learn from it costs time and money.
When's the best time to ask for feedback?
The book suggests maybe when the model itself has low confidence or when the system detects a likely failure. Or maybe offer users comparative choices, which of these two responses is better.
But you have to be careful, right? User feedback is user data.
Absolutely. Privacy and security are paramount when handling any user feedback. It needs to be treated with the same care as any other personal data.
Wow. Okay, that was a lot. We've covered the whole stack, really.
Yeah.
From understanding the foundation models themselves
Their data needs, scale, sampling, post-training,
to the kinds of problems they can solve in education, data organization, automation.
and then the deep engineering required. Evaluation, prompting, RAG, agents fine-tuning, data engineering, optimizing inference.
Building the architecture, monitoring it, and closing the loop with user feedback.
It really shows how AI engineering blends cutting-edge model understanding with solid software and systems engineering principles.
And the book really drives home that despite all these amazing applications, we're still just scratching the surface. It's still early days for this field.
The pace is just incredible. New models, new techniques, new challenges pop up constantly. It's hard to keep up.
It really is.
Yeah.
So maybe a final thought to leave everyone mulling over is this. Given everything we've discussed, the probabilistic nature of these models, the inherent fuzziness of evaluation, the risks like model collapse, the sheer speed of change.
Yeah.
How do we, as engineers and builders, ensure the AI systems we create are not just functional, not just clever, but truly reliable, controllable, and built in a way that they can evolve safely and align with human values over the long term?
That's the central question, isn't it? It requires constant learning, deep thought about design, and really understanding both the technology and its impact.
Indeed. A lot to think about. Thanks for joining us on this deep dive into AI engineering.